So this is recycling aluminum in resource-scarce regions. So my problem statement was to develop a cost-effective, off-the-grid aluminum melting furnace that can melt 1,200 aluminum cans per hour on a 12-hour duty cycle. And 1,200 aluminum cans is about 35 pounds of molten metal. This project first stemmed from the fact that there's a major trash problem in Haiti, even before the earthquake. They just don't have the resources and infrastructure to deal with trash, especially in rural off-the-grid communities. So I wanted to develop a system that could process and refine one of the most commonly found and problematic materials, aluminum. I set out some design criteria to limit the scope of my project. I wanted my system to be able to refine 1,200 cans per hour, including refueling, cleaning out the furnace, and all other maintenance. Then I constrained myself by saying I would only use commonly found materials with minimal equipment for the construction and use of the system. Then I set a budget of $100 so that one person could fund this project or a community could pull together some money to buy this. I then did some preliminary research. I found that most consumer products could only melt 1 or 2 pounds of metal at a time and would cost around $350. Then I found a YouTube video entitled How to Make a Mini Metal Foundry. The system is comprised of a steel bucket, lined with plaster and sand. Inside is charcoal. Surrounded by charcoal is half of a fire extinguisher. A top is made out of the same material that the lining is made out of. Forced air comes from the side, powered by a blow dryer. A hole in the top is made so you can input the raw materials and turn them into molten aluminum. Even though the system is simple, it can melt aluminum. I then did some secondary research. I found gas-powered crucible furnaces, similar to one I made, cupola-style furnaces, which is more of an upright system, and then reverberatory furnaces, which they mostly use for industrial recycling aluminum. I then developed some more in-depth possible solutions, each addressing some of the problems I had with the preliminary prototype. The first was airflow. I couldn't get enough airflow to the charcoal, as with the initial one injection point, it would only get half of the system hot. The second was efficiency. With the crucible-based system, you had to take out the crucible, dump the molten aluminum, which is also a safety factor, and then put it back in. That loses heat and time. The third was safety. As mentioned before, you're handling hot molten aluminum, so protecting the operator from the hot coals and the molten aluminum is a big factor. From these possible solutions, I came up with my final design. How it works is raw materials come from the top into the crucible, and from the bottom comes forced air heating the charcoal, and out comes refined aluminum from a controlled spout. The system is comprised of an air chamber at the bottom. Next is the middle and lower main chambers, which cradle the outflow pipe. Next is the upper main chamber, which sits on top of that. And on top of that is the top, with 2 holes, one for exhaust and one for inputting raw materials. Inside the system is a crucible stand, made out of 1/4-inch steel. Filling the system is charcoal. And surrounded by charcoal is the crucible, made out of half of a used nitrogen gas tank, which is 1/4-inch steel too. From the bottom comes forced air, and out the top is the exhaust for the forced air. The system is made out of mortar cement and perlite, forming a lightweight refractory material. The total cost of the system comes to about $80. To see if my system would actually work before I built it, I used a SolidWorks thermal analysis to test for thermal spread, deformations in the material, and a system thermal analysis, such as contact points. So to see if my system would actually be cost effective, I did a quick calculation to see how much charcoal per hour the system would use. I came up with a number of about 4 pounds of charcoal. This was consistent with what I saw with my preliminary prototype. So then I actually manufactured it. So I used rapid prototyping techniques, such as the plasma cutter, to quickly create iterations of my design. I then cast it in with perlite and mortar cement, using commonly found materials such as plywood and hot glue. So my foundry exceeded my expectations. It almost reached 900 degrees Celsius, and the melting point of aluminum is about 650 degrees Celsius. So how will my system actually affect somebody? So assuming the cost of charcoal is about $2 a pound, then you can make about $240 a day, or about $20 an hour. And that's amazing when you consider that most people in Haiti live on less than $2 a day. So it's one thing for me to say that I've built and tested this design. It's another thing to say that people actually want to use this. There's a small community in Haiti called Peninsula Arba Haiti. It's in the north and a bit inland. They want to actually use and implement this system in their community. So I'm actually going to Haiti and training the local Haitians to build and maintain this system. It's one thing to give them the system and say, hey, this will better you. But it's another thing to say, this is how it actually works, and this is how you maintain it once I'm gone. I'm applying for a US patent and in the process of pursuing sponsors for the implementation of this project in other resource-scarce regions. I'm also looking into other ways to implement this system in older technologies, such as wood gasification, where you take smoke, basically, and you put it into an engine. And this has been Recycling Aluminum in Resource-Scarce Regions.